All right, so the first important thing you learned about fluid at rest was that, so here's a fluid at rest. And at this point, the pressure is atmospheric pressure, and as you go deep in the fluid, the pressure at this location is atmospheric pressure plus rho GH. Okay. My apologies, I'm using a surface, but I hadn't used the surface in a while, and I guess the pen doesn't seem to be charged. For some reason, it's erasing. Okay, but anyway, so the first important thing we learned was that the pressure in a liquid increases with depth. Okay, and H is how deep you are. Okay, so the next important principle we are going to learn is Pascal's principle. Okay, so now what we'll do is we'll enclose a fluid. So here's a typical application. Okay. And you know that the pressure is increasing with depth. So I'm just going to make up some numbers. Okay, so let's say the pressure at this point is 100 units. And at this point, it's 150 units. Okay. Now what I'm going to do is, so this fluid is enclosed, and I'm going to apply a force here and increase the pressure. I'm going to apply force, and the increase in pressure will be that force that I've applied divided by this area. Okay. And so increase force divided by the area. And so let's say I increase the pressure by 30 units. So now the pressure here has gone up by 30 units from 100 to 130 pascals. And so what Mr. Pascal realized is that at every point in the liquid, the pressure will increase by the same amount. So the pressure here will go to 180 units and so on. Okay. So that's Pascal's principle. Okay. And so that's what Mr. Pascal's law states. A change in pressure applied to an enclosed incompressible fluid is transmitted undiminished to every point in the fluid. So if you, by applying a force, you can increase the pressure there by F1 over A1, and that will be the increase in pressure at every point. Okay, so you increase the pressure at that location by F1 over A1, and so that should be the increase in pressure at that location. Except that this area is much larger, so this force, F, since A2 is much larger, F2 has to be much larger. Okay, so that's the idea behind this hydraulic jack. You apply a small pressure here, and you get a much higher force here. So you apply a small force here, you get a much higher force. So this is essentially a force magnifier. So for instance, if this area were 100 times this area, so if this area were 100 times this area, if A2 was 100 times that, F2 will have to be 100 times F1. The output force will be 100 times this input force. So you can apply a 10-pound force and lift a 1,000-pound object. Okay, so that's the idea behind this hydraulic jack. So the question is, what is the price you pay? Well, the price you pay is the following. If you move once 100 centimeters here, you have to move this 1 centimeter, you have to move 100 centimeters in that example. Okay, so that's the price you pay. But anyway, so Pascal's law is a change in the pressure applied anywhere to a closed fluid is transmitted undiminished. So that change will be the same everywhere. So the change in pressure applied to an enclosed fluid is transmitted undiminished to every point in the fluid. All right, so The output force is A2 over A1 times F1. Okay, again, so A2 is 100 times bigger than A1. If this number is 100, then F2 will be 100 times F1. The price you pay is X2. The distance, the output distance is 100 times the input distance. Okay. All right. Okay, and so now we'll talk about something called the buoyant force. Okay, so here's the idea. You guys saw that all right, so you guys saw that the pressure in a fluid increases with depth. Okay, so now let's take an object like this. The pressure here is greater than the pressure here. So the force is pressure times area. So this force at the bottom will be greater than the force at the top. The force that the liquid exerts at the bottom so I can't find my tools here. Okay. So the force at the bottom. Okay, I have lost the pen. It's not writing. All right, my apologies. This auto rotate on, but okay. Anyway, so coming to this, so since the pressure increases with depth in a liquid, the pressure at the bottom is higher than the pressure at the top. That means the force at the bottom will be higher than the force at the top. So anytime you immerse an object in a fluid, you get a net upward force. The fluid exerts a net upward force on the object. Now, this is possible only in a gravitational field. Uh, so for instance, if you did this in space far away from any object, you wouldn't have any buoyant force, okay? So to experience a buoyant force, you have to be in a gravitational field. Okay, so again, if you immerse an object in a fluid, you experience an upward force. So there's the force of gravity on the object, here is the buoyant force. And so if you weigh this object in air and then weigh it in liquid, in a fluid, it will weigh less by that amount, by the buoyant force. Okay? So buoyant force is an upward force exerted by a fluid on a partially or fully submerged object. It's a result of increase in pressure with depth. Okay? So Uh, so let's look at this simulation. Let's see. Okay, why can't I go there? All right, so let's all right, so this block of wood, the block density, so the block of wood is feeling a buoyant force, and the buoyant force, it turns out for this piece of wood, the buoyant force is equal to the weight of the piece of wood, and so it floats. And now if you increase the block density, so this is in water, if you increase the block density greater than the density of the fluid, now the buoyant force was less than the weight of the block, and so the block sunk. Okay. Now we'll make it again equal. Okay. So now when the density of the block match the density of the fluid, okay, the buoyant force is equal to the weight of the block, and you see that now the net force is 0, and it will hover there. Okay, so the net force is 0 and it will remain at rest. And our body density is almost equal to the density of water. And so if you don't flail around in underwater, you could suspend yourself in water, sort of. I mean, so essentially, okay. All right, so this buoyant force arose because the pressure increased with depth. Okay. All right. So Mr. Archimedes gave us a formula for exactly how big this buoyant force is. Okay, how large this buoyant force is. And Mr. Archimedes tells us that the buoyant force is equal to the weight of the displaced fluid. What that means is, see, this object displaced that much fluid, and the buoyant force is equal to the weight of that much fluid. Okay, so this was a fluid, and the buoyant force is the weight of that much fluid. Okay. So the buoyant force is the fluid density times the displaced volume times the acceleration due to gravity. That's the weight of the displaced fluid. Okay. So what is the apparent weight of this object underwater? It's the force of gravity minus the buoyant force. Okay, so the apparent weight is the actual weight of the object minus the buoyant force. Okay, so underwater, for instance, the buoyant force on a person is almost equal to their actual weight. So their apparent weight was essentially 0. Okay, so underwater, you're weightless. Okay.
For a floating object, for an object that is floating, if you want to know how much of the object is immersed, it turns out that the object density, so the density of the object divided by the fluid object, and the density of the fluid is equal to volume displaced by volume of the object. So what that means is, so if, so for instance, for ice cubes, the object density is 90% that of the fluid of water. So the density of ice is 90% that of the density of water. So 90% of an ice cube is underwater. That's what that means. The volume displaced is divided by the volume of the object. Okay. So about 89% of an iceberg is underwater. So 90% of the iceberg is sunk underwater. Okay. All right. Again, I will pause again and let you guys ask questions if you have any. And we'll pause for 2 minutes. Okay.